Handing over. Thank you. Hi everyone, I'm Morgan, and continuing on with the theme, I was originally a mining engineer. Now, what's a mining guy talking at a space conference for? I came up with an idea in 2015 that I couldn't break, try as I might. And so I've come today to ask for a bit of help. So we're going to start with a video of the concept, talk about how it fits in the propulsion picture, see how it applies to CubeSats, and then we'll talk about exactly how we're going to do that, because there may be a few questions. And let's see if this works. Ooh. Cool, right? So, 20-ton ISO 668 standard shipping container. That's the goal. We want to move existing logistics into space. This will suit mining, this will suit minerals extraction. We believe we can manufacture over 90% of it domestically here. And what you just witnessed was particle accelerator electromagnets pushing something big instead of something small. So if I can get this to go back, we'll do it once more, just so we're all on the same page. I'm going to see where we fit in the propulsion picture. Now, strictly speaking, because this is a whole room of engineers, and I love that, that video functions in reverse. Realistically, the middle layers stay where it is, and the bottom layer seems to absorb the recoil, which is then offset with electric thrusters. As you're dividing it out through the structure, you can drop that velocity incredibly. There's a few other levers we can pull, but let's talk about how it fits in the picture. So we use liquid fuel rockets to get off Earth, and it's great for that. But they have very heavy centralized infrastructure requirements. And we can't manufacture liquid fuel on the moon yet, but one day. So for now, electric propulsion is our single best way to get around in orbit. And I have no doubt that that's actually going to continue to be. 1 kilo xenon, or naphthalene perhaps, could go an incredibly long way in high ISP systems. And so where do we fit? We're looking at distributed propulsion. We're looking at collecting as much force as possible to push objects between orbits. This is not in orbit or intra-orbit. This is inter-orbit. Now, how does that apply to CubeSats? You're like, cool, great, mate. But what does it do? You want to start with shipping containers. I originally wanted to start with an asteroid. I figured if I can catch and cook an asteroid, we can enable off-Earth mining. However, yes, big promise, right? So let's go smaller. Let's start with a shipping container. Now, the same concept we can use scale down to apply to CubeSats. Now, we'll go through, we'll look for a singular number that everyone can apply, and I'll get to that in a little bit. But our initial premise for CubeSat systems, we want to act as an accelerator. You come to our platform, we provide Propulsion-as-a-Service. And that allows you to send your CubeSat and preserve your onboard propulsion until you get to your destination, or if you keep going, or you want to pull a Hayabusa and come back for another look at something different. The other option, low-cost transport for mass rideshare, or as a comms relay. So we are aiming to build the freight railroad of the future. We're going to place this in multiple destinations. It is mass producible, and that lends it greatly to being a comms relay. But how are we going to do this, right? I've said a whole bunch of stuff. It all seems wonderful, magical bouncing satellites, and that's cool. But as I said, this came from particle accelerator technology. I considered that we've used particle accelerators for a very long time, but we haven't really changed too much. So this is a construction of well-known existing technologies, just applied in a different setting. We've got a yoked pulse solenoid, and beneath that, 151 kilos of lithium. So I am not a CubeSat system, so thank you for the invite still. Control components beneath that, and then the same solenoids are used in a smaller version in the XY plane to get you your central anchoring. That combined mass is what allows you to then shift the momentum instead of looking at a mass consumable system. So we looked at exactly how much force could we start to generate. And figure 2 is a braided cable. We've used the same cable since the 60s, which have worked pretty well. We're now using them for fusion research. The part that we didn't use since the 60s but knew about was niobium tin. We couldn't manufacture it with the right properties to actually make it a consumer wire into the right way, but thankfully a lot of that's now been fixed. And you'll see in figure 3 an example of an almost 80 Tesla spike in a fraction of a second from a multi-coil solenoid. Now for reference, if any of you have been for an MRI, they go to about 3T in super high-powered systems. So this is giving you a little perspective. Now, how does it work? Because originally, you kind of go, yeah, okay, cool video. The math sort of might add up, but how can I apply that? How can I check that this is something we can use? So for the next section, we're going to work through the math quickly. We are going to look for a single number that any system or mission designer can use, and then we'll talk about where the project's currently at. So traditional electric propulsion, you've got a consumable mass, push it out the back of your satellite, apply a force, and from there, you get thrust. But what do you do if mass is constant? You know the velocity change up equals the velocity change down. This has to be equal and opposite. Let's say you've got a 20-ton container, you've got 4 5-ton satellites. If each satellite pushes up 1, your container moves up 4, each of your 4 satellites move back 1. Now, that's ultra simple, and I don't expect anyone to actually be digging through running these. But if you understand the momentum, and you can see how you can use momentum change with constant mass, you can then start to see where our system applies. So the real answer that I want to give you is just how much magnetic pressure we can apply to the face of your CubeSat or another object resting on top, as you saw in the Bogong assembly. Now, I mentioned that xenon thrusters are planned to be used for the bottom, for the swarm reset, but we're keen to use whatever leading technology is available at the time. So we're looking at Moon to Mars and advanced manufacturing, trying to get as much domestic integration as possible. But enough of that. So, quick method. How's it work? Magnets create pressure. Pressure across an area gives you the force. You know your mass gives you acceleration. And for small systems, you can start to see, like, we might be able to feasibly give you this huge initial push to send you to a deep space mission. Now, when you look at a solenoid's field strength, it's based mostly on the geometry. Now, without really digging into detailed electrical engineering, I want to give you a simple number, 3.62 MPa. 3.62 MPa times your area, divide through by mass, gives you your acceleration, and you're able to see that we could give you a huge initial push. The real answer, if you actually want to go and sit and go, hold on, 3.62 MPa sounds way too easy, I can do it on my phone, it's an upper bound estimate. So you've got to go looking for the induced current. Now this comes from a textbook, Case Studies on Superconducting Magnets by Yukikazu Iwasa, and the force of a thin solenoid acting against a ring coil. You go looking for your generated field, reaction against your induced field, and then a few other factors, distance, alignment, all comes out pretty neat. Not so much fun to do on your phone. Now, what do the results look like? Because let's be real, that's the one that you actually want to see. As we start to scale swarm size, you see a significant drop-off in the power utilization. Now, we published a public reference design, and this is something that everyone can use to validate our numbers and theirs against. But as you can see, the results converge pretty severely on the right-hand side, and they start dropping significantly on the left. So an optimization point is very early in this chart, and it starts to look like we could use a much smaller magnet, much more xenon, and have more utilization. So speaking to an earlier point about what is your overall mission? Our overall mission is to build the freight railroad of the future and have it there stable for as long as humanly possible. And you can see, if we start scaling up and continuing manufacturing, it starts to look pretty good. So, where is the system currently at? I'm doing my PhD at UTS. I was a UNSW undergrad, but I'm now studying under Professors Caroline McGregor and Paul Kennedy in quantum secure satellite comms to speak to an earlier security point someone raised. Now, system modeling will continue. I'm into digital twins, and we are trying to raise funding for the prototype. Hardware will come from the startup and funding. Software will come from our research. And hopefully if we can raise this year, we'll have a prototype operational next year to validate. And then as short a turnaround as possible to manufacture 10 and get to MVP. If manufacturing continues, we scale speed, we scale the number of routes. So this is reasonably feasible. We use existing technology. Unfortunately, it is a little expensive. As a mining engineer, that's what we're trained to deal with, the amount of cost and unknowns. But I just wanted to say thank you for this opportunity to come and talk to you about how much pressure we can apply to your CubeSats. So 3.62 MPa, everyone. Thank you for your time. If you'd like to know more, check out our website or come grab me.